So in each of the units of calculus we've done, we've had an application of integrals to kinematics. Do you remember going from displacement? The derivative of displacement is velocity. And the derivative of velocity is acceleration. Sva. Such a nice.
The derivative of acceleration is jerk.
Oh, there we go. So now, since we've learned sva, we can also learn avs. Avs. So we have derivatives working one way, integrals working backwards, and you'll find on your exam they like to mix these things up, so you'll get a kinematics question where part of it you have to do derivatives for, part of it you're going to have to work backwards and use integration. So this is what we've seen already, and this is just saying again that velocity is the derivative of displacement and acceleration the derivative of velocity. So now we can start our question with an acceleration formula. The acceleration of a particle is given by t plus 1. Find the equation for the velocity and the equation for the displacement, and they give you some extra information. The nice thing about doing kinematics is it's basically a review of a lot of the concepts we've done already. So if I want to work backwards, right, from acceleration back to velocity, I'm going to have to integrate. So I could write that velocity is going to equal the integral of t plus 1 of my acceleration dt, and that is a really easy integral to figure out. And what do I have to do with an indefinite integral? Plus c. Are we done with our velocity equation, or can we find c? Do we have enough information to find c? So if we think back in our notes when we had questions like this, finding c earlier, we needed a point. Do we have a point or something telling us some information about our velocity? Yes. At the very end there it says when the time is 0, our initial velocity is 8. So we can plug in 8 for our velocity, 0 for our time, and calculate that c has to be 8. So our final velocity equation is right there. And if we want to find our displacement formula, it's going to be the integral of our velocity formula add 1 to the exponent, divide, add 1 to the exponent. And what do I need to add here? Plus d. We used c already, so we've got to be careful here that we don't use the same thing twice. And we're also told that at time 0, s is 0. Are you okay with this quick mental math? Yes? When s is 0, t is 0, so you plug in a whole bunch of zeros, and all that's left is d. And so our final equation for our displacement is just like that. Try this one. Acceleration. Oh, pen is down. Did you do the derivative? If you integrated, it's tempting, right? You have to remember which direction you're going, integrate or derivative. And then the initial displacement is 40, so here we're going to need to do the integral. Find the value of c. No problem. So our velocity is going to be the integral of our acceleration. We have an initial velocity, so we can solve for c. And you get t squared minus 4t plus 3. Finding the displacement, we integrate here. I guess I could have gone plus d. I used plus k this time. The letter really doesn't matter which letter you use, as long as it's different than c.
You lose like the extinct letter.
Sure.
What Arabic letter?
Just some random letter that you've invented.
You think they would accept that?
They would have to. You can make whatever symbol plus happy face, where happy face is an element of the reals. That would be fine. Right? Then you find out that happy face happens to equal 2. So we've got our displacement. Find the values of t when the particle's at rest. So what does that mean?
When the velocity is 0.
The velocity has to be 0. So when we have something, like if I throw a golf ball up into the air, there is a moment when it gets to the very height that it got that it stopped, because it changed from going upwards to coming back downwards. And at that moment, we would say the golf ball was at rest. Now, I'm not saying that if your siblings are tired, you should put them at rest by throwing them up in the air and say you've got a moment of rest at the top there. So we said our velocity equals to 0. Factor that equation, we get 3 seconds and 1 second. Did you remember to include your units?
Yes.
Okay, good. Find the displacement of the particle at these times. So now we need to take 3 seconds and 1 second and plug it into which equation? Our displacement equation. Did you remember units on this one? No. Yes.
So, if a paper reduces to negative, that means it's just near rest.
Most of our displacement acceleration questions are fairly straightforward, although on the last couple of exams, they've been doing some interesting things. There was one exam, where you had a velocity graph. Let's say this was your velocity graph. From there to there. Okay. And it said, find the maximum velocity. So what did most people find? That point right there. Does that make sense? And it's this one right here. Why would that be a maximum velocity? Because it's still, what does a negative velocity mean? Just going in a different direction, right? If you have a velocity going upwards and a velocity going downwards, you could still say the downwards velocity is faster or larger than the upwards velocity. Okay? Whew. Would they catch you on that one? Almost. I like that. Okay? And then the other thing that has been coming up a fair bit on exams is the difference between distance and displacement. So if I take this golf ball out again, right, and I hold it in the air right here, I throw it up in the air, and I catch it exactly where I threw it from, what's the displacement? Zero. It hasn't gone anywhere, right? But if I talk about the distance, it's gone up a meter, down a meter. The distance that it's traveled is 2 meters, right? This idea of displacement and distance is why I don't like running. Because if I leave my front door and I go for a jog, I eventually get back to my front door, and my displacement is 0. And I'm like, I could have done that a lot faster had I not gone for the jog and just stayed at home, right? Easier. I'm not sweaty, I'm not tired, right? I'm not in shape, but that's not a problem.
Just don't go back to your house ever.
Just leave and just keep running. Just keep increasing the displacement. Right? Eventually you would hit a maximum displacement on the Earth.
Then you gotta go.
Right? You start building a staircase that just goes higher and higher. And there we go. So what we need to do is we need to figure out where our displacement is negative and where it's positive. So here we know that our displacement is our integral of our velocity. But as I threw the golf ball up in the air, it had, say, a positive velocity going up and then a negative velocity going down. So we have to think about our velocity graph. Part of it might be below the x-axis. Whenever that velocity is negative, when we do the integral, it would calculate the area, and that area would be negative, and we need to put absolute value bars around that section to count it as positive. Because I threw the ball up in the air, it went +2, -2, 0, right? We just need to put absolute values around that -2 part to count it as positive. So here's an example. Nice. Trying to think what kind of situation would have a velocity which would be a sine graph in it. So the velocity is given by 1 minus 2 sine 2t. Find the object's displacement. So here it's displacement. Life's going to be easy because we can just find the regular integral from 0 to 3 pi over 4. I forgot the dt here. Right? The integral of sine is a negative cos. So we have a -2 sine. So we should get a positive cos. Where did the 2 go in front? Right? This 2 in front just disappeared. Right, because we have a 2t inside. So there would have been a chain rule if you're doing the derivative to multiply by 2. So when integrating, you would have needed to divide by 2. It's not bad. If you had left the 2 out here and divided by 2, I actually don't mind doing that because it helps me see where everything comes from and I can simplify it afterwards. Plug in 3 pi over 4, plug in 0. We have to know our pi plate values. And we get 3 pi over 4 minus 1, which is approximately 1.36 to 3 sig figs. Now this is the displacement. If we wanted to find the distance, and usually these are questions that you have access to your calculator, but I think, how could I use my calculator best to figure out this distance? So first of all, let's take out our calculator and graph this. Let's go to y equals, clear it out. I'm going to put that velocity equation into our calculator. 1 minus 2 sine 2t. And we are trying to figure it out for the first 3 pi over 4 seconds. So I'm going to go to my window, and I'm going to go from -1 just so that I can see my y-axis. I'm going up to 3 pi over 4. So I'm going to go up to pi just to see a little bit more. But I'm going to make my scale pi over 4 so I can really see where 3 pi over 4 ends. Okay? If I hit graph at this moment, my y values were from -10 to 10. They actually turn out not too bad. Yes? Why didn't I go from 0 to 3 pi over 4? I could have. I like to see if I go here, I'll go back to my window. If I would have started at 0 and I hit graph, well, it still shows the x-axis. Sometimes I like to see more of the x-axis. And sometimes I like to see a little bit on either end. But if I wanted to see exactly from 0 to 3 pi over 4, that would be fine as well. So there's our graph. We notice that some of the velocity is positive, some of the velocity is negative. So when we integrate this, can you see that the red area is going to be negative, but the purple and the blue areas are going to be positive? So if we were writing things out, we would need to find out where those x-intercepts are. Yes? If we graph the derivative that we get, okay, we have to find the definite integral to find out its area under that curve. And wherever the area is negative, if we do it all at once, it'll just subtract that area, which is what we did in part A, 1.36. What we're going to do with this graph is we're going to use our calculator's built-in integral to figure out the different sections. Okay. Mm-hmm. What's this 3 pi over 4?
Yeah.
Well, we're doing the definite integral, which starts at 0 and goes to 3 pi over 4. So when we do the definite integral, we don't do plus c. We put it in square brackets and put the bounds that we're finding it right after the square brackets.
Okay. So that's not an exponent.
No, it's not an exponent. It's just the 0 and the 3 pi over 4 are these same bounds that are on our integrand sign, integral sign. Okay. So then we could rewrite this for the distance to say the distance, which I'm using x, the distance is going to be the integral up to pi over 12. Then from pi over 12 to 5 pi over 12, then we have to put absolute values around it because that area is going to be negative. And then from 5 pi over 12 to 3 pi over 4 after that. So I would like you to go to your calculator right now and see if we can figure out each of these separately. So on my calculator, if I go second calculate, and I want to go to number 7, the integral, starting at 0 and going to pi over 12. It finds that first area, 0.128. If I want to find the second area from pi over 12 to 5 pi over 12, that area should be negative. And then when we take the absolute value, it will be positive. Yes? What's that? Yes, we're going to find it all at once at the end. I'm splitting it up right now so we can see each of the parts separately. Okay? And so the last section would be from 5 pi over 12 all the way up to 3 pi over 4. And if we figured out all of those separately, those would be the values we'd get. Add them together, and we get 2.73 meters. Now going back to our calculator, someone said, is there a way to do this all at once? Well, the problem with what we have right now on our graphing calculator is part of that area is below. How could I make that area go above? I could take my original function and put it in absolute value. So I'll have to rewrite it 1 minus here. I'll just clear. Okay. Here we go. Okay, absolute value. It's under number, the first one, of 1 minus 2 sine 2x. And now when I graph this, what does it do with that part that was below? Flipped it above the x-axis. And if I calculate my integral all the way from 0 to 3 pi over 4, all of those values will be positive, and we get 2.726 or 2.73 that way as well.